Okay, determining a chemical formula from experimental data. We talked about what an empirical formula is. It's the lowest ratio of elements. This is the type of formula that we can get by experiment. So the masses of the elements that are formed when a compound is decomposed. So we can take a compound, decompose it into its individual elements, weigh those elements, and from that we can calculate the formula of the compound, the empirical formula. We can also look at the masses of elements that react together to form a compound. And we're going to do that in an upcoming experiment. So we measure the amounts of the elements as they combine. Another way we can calculate this is using the percent composition. So the empirical formula gives us the ratio of atoms or the ratio of moles of atoms, again, not the masses. So how do we do this? So there's some steps here, and none of the steps is hard, but sometimes it's a little tricky to remember, what do I do next? So you just need to practice these. The first thing is we need to start with the masses of each element. Sometimes you're just handed those masses. Sometimes you have to figure them out. You might get the mass of the compound and the mass of one of the elements. And you have to figure out what the mass of the other element is. You do that by subtracting. Sometimes you're given percent composition. Then you're going to convert the percentages to grams by assuming that you're starting with 100 grams of the compound. It doesn't matter the size of the sample. The percent composition and the empirical formula are going to be the same. So we can choose a sample size that makes things easy. If we choose 100 grams, then the mass of each element is the same as the percentage. So all we have to do is take the percent off and write gram. Next step is to take those masses and convert them to moles. We've learned how to do that. You're just going to use the masses on the periodic table. I disagree with this step a little bit. It says write a pseudo formula using the number of moles of each element as subscripts. You can do that if you want to. I think it's a little silly, but it's fine. Divide all the subscripts by the smallest one. So when I do this, I skip step 3. I divide all the moles of elements by the smallest, by the smallest moles. And I'll show you that in my examples. If you get a whole number, awesome. Many times you don't get a whole number. Especially if this is real data, there's random errors and things get a little messy. So how do you know if you can round to a whole number or not? My guideline is if your result is within 0.2 of a whole number, you can round. So if you divide the moles by the moles and you get 2.1, that's within 0.2 of the number 2, the whole number. You can round it. If you get 2.23, that is not within 0.2 of a whole number, so you can't round it. If you can't round it, you're going to have to multiply all the subscripts or all the moles by the same number until you get whole numbers. So some of you will recognize the decimal equivalence of fractions, right? 0.75 is 3/4. Well, if you take this and you multiply by the denominator 4, you're going to get a whole number. 0.25 is 1/4. Again, if you multiply by 4, you're going to get a whole number. So if you recognize that, awesome. If you don't, go with trial and error. So try 2. Multiply the number by 2. Is it within 0.2 of a whole number? Great. If that doesn't work, try 3. Then try 4. You rarely have to go past 4. Those are the rules. Here's an example. Sample of a compound is decomposed in the laboratory, produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula. So, first thing is write down the masses of each compound. So 165 grams of carbon 27.8 grams of hydrogen and 220.2 grams of oxygen. Here we're given the masses, so we don't need to do any changing of percentages to grams. Next step is to convert these to moles. So I'm going to multiply by a fraction that has moles in the numerator and grams in the denominator. And this is the molar mass, and we find that on the periodic table. So for carbon, it's 1 mole to 12.01 grams. And we do the same thing for each of the elements. So for hydrogen, it's 1 mole weighs 1.008 grams. For oxygen, 1 mole is 16.00 grams. So we see that the grams cancel, and we get moles. So my starting number here had 3 significant figures. You definitely do not want to have rounding errors when you do a problem like this. So having more digits is better because it's going to end up with whole numbers at the end. You don't have to keep track of sig figs as long as you keep lots of digits. I'm going to keep track of them because I'm kind of nerdy that way. So 3 sig figs, and I'm going to keep 2 extra digits to avoid rounding errors. So that's moles of carbon. And hydrogen, 27.579 moles. And oxygen, 13.7625 moles. Any questions yet? Yeah.
Could a rounding error occur when you use 16.00 and not 16.00?
That's an excellent question. So this is, I've rounded my my molar masses to 4 significant figures. Is that going to cause a rounding error? No, it shouldn't. If you round it to the nearest whole number, that may cause issues. It kind of depends on the element, but I would say never use fewer than 4 sig figs in your molar masses. Using more is better. The reason I go with 4 is because I've got a lot of them memorized, and it's good enough, and so it makes lecture go faster. Everybody likes lecture going faster, right? Yeah. So we have to get to moles because moles has to do with numbers of particles, and the formula tells us ratios of particles. It doesn't say anything about mass. That's why we have to get to moles. So you could make a pseudo formula here. It would be C 13.738, H 27.579, O 13.7625. I don't see the point, but the book does it. What we need to do is we need to make these into whole numbers. And so what we're going to do is we're going to find the ratio of these numbers, because these are messy numbers. So we're going to find the ratio by dividing each of them by the smallest. So we identify which of these is the smallest. Well, it's the moles of carbon. So I'm going to divide each by the smallest number. And of course, one of them is going to end up being exactly 1. So this is 1. I'm going to take the moles of hydrogen, divide by the moles of carbon. So 27.579 divided by 13.738 equals. So that's giving me 2.0074. So I can already tell that's a beautiful number. I can round it to 2. The 7 and the 4 aren't really needed there. And then here we're dividing this one by 13.738. And that gives me 1.0017. These two ratios are within 0.2 of a whole number. They're actually within 0.01 of a whole number. So we can round this to 2, and we can round this to 1. So we have whole numbers. Those whole numbers are the subscripts for the elements in that formula. So C1H2O1, except that we don't usually write the ones. So we write that as CH2O, and that's our empirical formula. Any questions? Here's another one, ibuprofen. I can ask my kids, this is my mom answer to any physical ailment. I have a stiff neck, take some ibuprofen. My glutes are sore from weights yesterday, take some ibuprofen. I have a fever, take some ibuprofen. Works for almost everything. That's an excellent question. What would my answer be if someone is allergic to ibuprofen? I'd probably go with aspirin. I have a thing against acetaminophen, Tylenol, because that's like so easy to overdose on. It'll destroy your liver and bad news. Ibuprofen, you overdose on that and you're going to get a nasty stomach ache and throw up and stuff, but no long-term damage. Much safer. I could tell you stories about my kids getting into medicine, but I won't. Ibuprofen has the following mass percent composition. What's the empirical formula? So here we're given percentages instead of masses. No problem. We're just going to write the percent down, and instead of writing percent, we're going to write grams. We can do that because if our sample weighed 100 grams, these would be the masses. So that just makes things easier. So 75.69 grams of carbon. 8.80 grams of hydrogen, and 15.51 grams of oxygen. Now we're going to do the same thing we did in the previous example. So I'm going to do this a little more quickly. We're going to go to moles of carbon, and we want to convert to moles of hydrogen. And moles of oxygen. $75.69 divided by 12.01. 6.3022 moles. 8.8 divided by 1.008. 8.7301 moles. And the oxygen, .96937 moles. So this is moles of carbon, moles of hydrogen, moles of oxygen. Here we have non-integer numbers of moles. We want whole number ratios. So we choose the smallest one, divide all of them by the smallest. We want to do the smallest because that way we won't end up with more fractions. Everything will be 1 or larger when we're dividing by the smallest. So this one is the smallest, and so that one's going to end up being 1. Take this one on the top, 0.96937. And 6.5013. And the hydrogen. 9.0059. So the 1 is awesome. That's an integer. The 9.00, that can be rounded. What about this 6.5? Can we round that to 7? No. So we need to multiply this by something to make it into a whole number. We're going to keep the ratios correct by doing the same thing to all of them. So you may recognize that 0.5 is the decimal equivalent of 1/2. So if we multiply by 2, we should get a whole number. Or 2 would be the place you start, just trying random things. So 6.5013 times 2, 13.00, some other things. Definitely can round that to 13. When we multiply this by 2, we're going to get 18 point some stuff. And when we multiply the 1 by 2, we're going to get 2. Any questions about that? If you take 18 divided by 13, you'll get the same number as if you take 8.7301 divided by 6.3022. We've just converted that ratio into whole numbers. Yeah?
So we multiplied by 2 because we couldn't round 6.5?
Yes, we multiply all of these by 2 because this cannot be rounded to 6 or 7. When we take this somewhat messy number and multiply by 2, we get a beautiful number. If we still got something ugly here, then we would try multiplying by 3 instead, or 4, until we found one that gave us a whole number, and then you do the same thing to each of them. Okay? So we've got our subscripts then, 13, 18, and 2. So C13, H18, O2. That's the empirical formula for ibuprofen. If you notice, these numbers here, this ratio 13 to 18 to 2, that can't be simplified, right? It's in its lowest whole number ratio. Sometimes students ask, well, how do I know which element to put first? Well, in problems like this, just use the same order that the problem gave you to start with, and that'll work out just fine. Any questions? Well, that's finding the empirical formula, but we often need to know what the molecular formula is. So the molecular formula will be some multiple of the empirical formula. In order to figure out what the molecular formula is, you're going to need the empirical formula, and you're also going to need to know what the molar mass of the compound is. So that would be determined probably using mass spectrometry. It's not something that we will be doing in lab. So when we do problems like this, the molar mass of the compound has to be given to you. So the molecular formula is the empirical formula times some integer. It's a multiple of the empirical formula. What we need to find is this n. Then that's what we're going to multiply all the subscripts by. So to find n, we're going to take the actual molar mass and divide it by the mass of the empirical formula. So take the empirical formula, find the mass of that, the molar mass of that, and divide them. And that should give you a nice whole number. There's no rounding or multiplying involved. Let's do an example. Compound has the empirical formula CH and a molar mass of 78.11 grams per mole. What is its empirical formula? So we need to find the number to multiply the subscripts by. So we're going to take the molar mass that's given, 78.11 grams per mole, and we're going to divide by the molar mass of this formula. So for CH, that's going to be 12.01 plus 1.008, which I think is 13.018 grams per mole. The units cancel out. 78.11 divided by 13.018. 6.0001. So that is 6. That tells me the molecular formula is 6 times more massive than the empirical formula. It contains 6 of the empirical formulas. So writing it this way can help us understand what we're doing here with that 6. This is not the correct way to write the formula, but it just helps us to understand. This is C6H6. Empirical formula had subscripts of 1. They were not written, but they're understood. We multiply by the integer, we get C6H6. You can calculate the molar mass of this. It'll come out to be 78.11. Any questions?
And if that answer was like, let's say 6.5, would we multiply that by 2?
Excellent question. What if this came out to be 6.5? If that were the case, then you calculated something wrong. You probably would have calculated this wrong because this should never come out to be anything other than a whole number. But a good question. Any other? No. It'll always give us a whole number. Any other questions? So combustion analysis is a common technique for analyzing compounds to figure out what their empirical formulas are. So this is really useful for organic compounds that contain carbon, hydrogen, and oxygen, and that's the only group of compounds we're going to talk about this with. So if we know the mass of the product and the composition of the elements in each of those products, we can figure out how much of that element was in the original sample. So when we're burning something that contains only these 3 elements, all of the carbon forms CO2. You can collect the CO2, and from the mass of CO2, you can figure out the mass of carbon that was in the original compound. All of the hydrogen in that compound forms water. So we collect the water, we measure its mass, we can figure out the mass of hydrogen. If the compound had oxygen, what we're going to do is find that mass of oxygen by subtraction. It's got carbon, hydrogen, and oxygen. We just figured out the mass of the carbon and the mass of the hydrogen. We needed the mass of the original sample, and then we can subtract to find the mass of oxygen. So this is an illustration of how combustion analysis occurs. So you've got a furnace. You put your sample in there. You would weigh it before you put it in there. Oxygen streams in here, and this is heated so that it burns. So it combusts, it reacts with the oxygen. When compounds containing carbon, hydrogen, and or oxygen burn, they always form CO2 and H2O. So we have a trap here, a tube containing a substance that will absorb water. So you weigh the tube before this starts. As this combustion occurs, there's a stream of oxygen going through, so all the water given off is forced to go out this way. It comes through this tube, and it gets absorbed. The CO2 does not get absorbed here, keeps on going, and it goes through another tube containing a different substance that absorbs the CO2. The tube weighs more after the analysis because it's grabbed the CO2. And so weighing those, we get the mass of CO2, the mass of H2O. We can't directly determine the amount of oxygen because we had to pour a whole bunch of oxygen in there to make it burn. Some of that oxygen went into the H2O, some of it went into the CO2, and the rest of it just goes straight through. But we can find the mass of oxygen by subtracting hydrogen and carbon from the original sample mass. So here's an example. Upon combustion, a compound containing only carbon and hydrogen produced 1.6 grams of CO2 and 0.819 grams of water. Find the empirical formula. So this is a similar idea to what we were doing before, but there's an extra step at the front. Because finding the empirical formula, we need the mass of each element. This compound contains carbon and hydrogen. We need the mass of carbon, the mass of hydrogen. But we're not given that. We're given the mass of CO2 and the mass of H2O. So we'll start with these grams of CO2. And we need to find the mass of carbon in there. So this is the sort of problem we did at the beginning of lecture. We're going to convert, maybe I'll write it down here. So the strategy here is we've got grams of CO2. We're going to convert that to moles of CO2. And then we're going to convert that to moles of carbon. Now you could convert that to grams of carbon, but then you'd have to go and convert it back to moles of carbon. So you can actually just stop here. So moles of CO2 over grams of CO2. So those units cancel. And then moles of carbon and moles of CO2. How many moles of carbon are in 1 mole of CO2? 1. So that's 1 to 1. How many grams? Oh, we got to do some math. So 12.01 plus 2 times 16 is this 44.01. That's the molar mass of CO2. So 1 mole of CO2, 44.01 grams. 1.6 divided by 44.01 times 1 over 1. 0.036355 moles of carbon. Here, it's very important to understand that these leading zeros are not significant figures. Sometimes you get a bunch of zeros at the front and people end up rounding this to one significant figure, and then that really messes up your formula. So I want to keep at least 3, and I like to keep 3 plus 2 extras. Any questions about that? We're going to do the same process for the water now to find the mass of hydrogen. So 0.819 grams of water. Well, we're going to convert that to moles of water. So we'll divide by grams of water. And then we'll convert that to moles of hydrogen and divide by moles of water. How many moles of hydrogen in 1 mole of water? 2. 2 moles of hydrogen to 1 mole of water. Then we need the molar mass of water. I know what it is, but we'll calculate it anyway. 2 times 1.008 plus 16, 18.016 grams per mole. So 1 mole of water weighs 18.016. 0.819 divided by 18.016 times 2. 0.090919 moles of hydrogen. In previous examples, these moles were fairly large numbers, and here they're small. And sometimes you'll have ones that are, 0.0000 something, very, very small. That's okay. The absolute size of these depends on the size of the compound sample that you started with. If you start with a lot, you're going to have more moles. If you start with a tiny amount, you're going to have fewer moles. The ratios end up being the same. Now that we have moles of each element, what's the next step? Divide by the smallest. Okay, so we're going to divide by the smallest. So that one ends up being 1. And this one, divided by the smallest, you can kind of guess what it's going to be, but we shouldn't do guessing. We should actually do the math. Because you might have guessed that would be 3, but it's actually 2.5. So 2.5008. What do we have to do? Multiply. So we'll multiply by 2. And that's going to give us 5.0017. So that's 5. I also have to multiply the other one by 2. You have to do the same thing, otherwise the ratio would change. So then what's my empirical formula? C2H5. Any questions? Here's another one. Upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen produced 1.6004 grams of CO2 and 0.6551 grams of water. Find the empirical formula. Okay, very similar idea. This one, though, there's oxygen. So we've got mass of CO2. We're going to get moles of carbon out of that. We've got mass of water. We're going to get moles of hydrogen out of that. But then to figure out the oxygen, we need the mass of carbon, the mass of hydrogen, and we subtract those from the mass of the original sample. Because it contains 3 elements, carbon, hydrogen, and oxygen. So if we take the whole mass and subtract the carbon and the hydrogen, then we get the mass of oxygen remaining. So this one's a little more involved. So oops. Okay. 1.6004 grams of carbon. No, that would be nice, CO2. So we need to convert this to moles of CO2. We already calculated the molar mass. So 44.01 grams of CO2. And then 1 mole of carbon for every 1 mole of CO2. So that gives me 0.036, 44 moles of carbon. And then we'll take the mass of water and find the moles of hydrogen. And there's 2 moles of hydrogen and 1 mole of H2O. So that gives me 0.07272 for 2 moles of hydrogen. Well, we need moles of carbon and moles of hydrogen to do the ratios, but we also need the masses so that we can find the mass of oxygen. So what I like to do is actually write the moles down here in the middle, because I'm going to need those later, but then continue on and convert to grams so that I can subtract that. So this many moles of carbon converting to grams of carbon would be 12.01 grams of carbon per mole. And this one would be 1.008 grams of hydrogen per mole. I'm going to do the bottom one because I still have that number in my calculator. So that's 0.073306 grams of hydrogen. And for the carbon, 0.0363644 times 16. No, not times 16. Times 12.01 gives us 0.436736 grams of carbon. So I need to get to grams of oxygen. So I have my whole sample, 0.8009 grams of my compound. And I'm going to subtract the mass of the carbon, and I'm going to subtract the mass of the hydrogen. So 0.8009 minus 0.436736 minus 0.073306. And I get 0.290858 is what my calculator tells me. If I'm keeping track of sig figs, whoops, it would end right there. Now I have mass of oxygen. Any questions about how I got the mass of oxygen? So I'm going to take my mass, 290858 grams of oxygen. I want to get to moles of oxygen, so I'm going to multiply by 1 mole over 16 grams. That gets me 0.0181786 moles of oxygen. Now I have moles of each element. What do? Divide by the smallest. Which one's the smallest? The oxygen. So I'm going to divide by the smallest one. So that one's going to be 1. And I'm going to take moles of carbon and divide by the smallest. Let's see what I get. And so that equals 2.00. That's definitely roundable. Is that a word? It is now. Just made it up. This other one, 0.072742 divided by 0.0181786 gives me 4. Awesome, I got nice whole numbers out of everything. So this is the subscript for carbon, 4 is the subscript for hydrogen, 1 is the subscript for oxygen. So it's C2H4O. is my empirical formula. Any questions? That's, kind of an involved problem. That's the sort of thing that shows up at the end of an exam as a show your work problem that's worth more points than the multiple choice. That was a hint.